Hey guys, welcome back. I am filming this first thing in the morning, so excuse my morning voice. So what we're going to be looking at today is we're going to be looking at experimental yields. So in our last chapter, we were talking about using stoichiometric ratios and balancing equations. So we're going to use that information now to help us to determine an experimental yield. Excuse me. All right, so success criteria for today: calculate theoretical yield and experimental yield, and then identify limiting and excess reagents. And we've kind of spoken a little bit about limiting and excess reagents, right? When things react, they react in a particular ratio. So if I had something that was reacting in the ratio 2:3, right, but I only had 1 mole of this particular substance, well, then that would mean that this would be my limiting reagent, okay? And then alternatively, we can talk about excess reagents. So like I said before, if we were doing things in the ratio 2:3 and I actually have the ratio 2:4, then this is actually going to be an excess amount or excess reactant. Excuse me. Quite often when we're talking about excess reactants, we're talking about things reacting in the presence of oxygen, because when you're, sitting and doing an experiment in the room, there's not an infinite amount of oxygen in the room, but you're not likely to run out of oxygen in the room. It's much more likely that you're going to be limited by the reactants that you have on hand. All right, so I really like this Murphy's Law. Anything that can go wrong will go wrong. And I feel like, if anything, the first day of term 2, 2020, that kind of really was true. So that's why I'm filming at home today. So very rarely, speaking of Murphy's Law, very rarely do we actually ever get a yield of 100% from a reaction. So basically, going back to this idea of the law of conservation, we cannot create or destroy matter. But sometimes when you have a reaction, the reaction doesn't go through to completion. So you might still have like 10% of your products left over. And as chemists or as scientists, we are perpetually looking to improve this process. For example, the Haber process, basically what they do is they take nitrogen from the atmosphere and then they fix it to the soil, and then we have nutrients that we can then give to plants, like fertilizers and stuff like that. And that process is something that we've been working on making faster and faster and faster for years. So really what we do is we look at the rate of yield, and we're looking at processes that improve that yield. So let's have a go at doing some yield questions. So the experimental yield is how much you actually got from doing your experiment. So let's say you got 90 grams of the substance, whereas the theoretical yield is the actual yield that you were expecting to get. So that will tell us what the percentage yield is. So here we go. First example, 39.7 grams of magnesium carbonate was decomposed in an experiment. 15 grams of magnesium oxide was formed. Determine the percentage yield of magnesium oxide. Okay, so for these kinds of questions, the first thing we're always going to do is we're going to write a balanced chemical reaction. So we've got magnesium carbonate. Magnesium is 2+, carbonate is 2-, so that's already balanced. And what does it do? It decomposes. So we've spoken a little bit about decomposition reactions. So oh, no, we haven't. Not yet. That'll be next. Sorry. Decomposition reactions are when things decompose into 2 or more different parts. So this is going to decompose into magnesium oxide. And then, as you can see, we've got 1 leftover carbon and 2 leftover oxygens. So that's just going to form carbon dioxide. Okay, so now let's balance this equation. I've got 1 magnesium on each side, so that's balanced. I've got 3 oxygens on each side, and I've got 1 carbon on each side. So luckily for us, it's already balanced. All right, so let's determine the percentage yield of magnesium oxide. So to do that, I'm going to use the molar mass formula. So I know that I have, if I was talking about the mass here, I've got 39.75 grams of magnesium carbonate. After it decomposes, I've got 15 grams of magnesium oxide. Now, what I can do is I can go to my periodic table and I can determine the molar mass. So I'll do that now. All right, I've just written a few things on the screen here. So I've written the molar mass for each of these compounds. I've always just got this equation sort of in the back of my head, and I've just rearranged that equation here so I can substitute those values in. All right, so now we're going to work out the number of moles. So for this one, we have, what's the mass? 39.75 divided by 84.31. So I'm just going to quickly chuck that in my calculator. 39, excuse me, 0.75 divided by 84.31, and that's going to give me 0.47 moles. So that's how much I have of this substance reacting. Now just quickly, because we already balanced this, we know that this is reacting in a 1-to-1 ratio. So what I'm actually expecting, I'm expecting to produce 0.47 moles of this as well. So I'm going to write this over here. So I'm expecting, I'm expecting that I'm going to get 0.47 moles of magnesium oxide. Okay, so let's go through now and work out the actual number of moles produced. Just out of curiosity's sake, we don't actually have to do this. Okay, so this number of moles is 0.37 moles. So they're not too far off. But this one, as you can see, is slightly higher than what this one is. Okay, so we didn't actually have to do that, but what we did actually have to do was we have to use this formula here. So we have to do the percentage yield is equal to the experimental yield divided by the theoretical yield. So theoretically, right, this is what we should have. So let's work out that mass. So again, just rearranging that formula. So the mass should be equal to 0.47 times by the molar mass. So let's do that. 40, oh, my calculator's dying. 40.3 times by 0.47. So I should have produced 18.941 grams. So let's just round that to 18.94. All right, so let's pop that in our formula. I'm going to give myself just a little bit more space. So this is our formula just here. So the percentage yield is the experimental yield divided by the theoretical yield. Now, we know that the experimental yield is going to be 15 grams of magnesium oxide, and we know that the theoretical yield was 18.941 grams. Oh, we were just going to round that, weren't we? Okay, so let's substitute that in our formula. So the percentage yield is going to be equal to the experimental yield divided by the theoretical yield times by 100. So that's going to be equal to 15 divided by 18.94 times 100. So I'm just going to chuck that in my calculator real quick. 15 divided by 18.94 times 100, make it a percentage, and we have 79.20%. So this is the percentage yield for this particular outcome. So for these, we are going to use mass to determine the experimental yield and the theoretical yield and the percentage yield and all that, because again, this is something that we'd actually measure in a lab. So usually what they would have is they would have some sort of like procedural thing, and they would say, okay, so if you mix this many grams of this and this many grams of this, you should get this many grams of this particular product. And then they go through and they do the experiment and they go, oh, actually, no, we only got 80% of that. And so then they go back and they review the process and they say, okay, so how can we improve this process so that we get a percent yield closer to 100%? So that's basically how industry works really with these things, or the scientific industry works. So what I want you to do is I want you to have a go at this question here. So magnesium oxide is formed when magnesium ribbon burns in the presence of oxygen, and just double check that equation there is balanced. Determine the theoretical yield of magnesium oxide formed when 12 grams of magnesium reacts with excess oxygen. When a student performs this experiment, they found 18 grams of magnesium oxide was formed. So again, see how whenever we're doing some sort of experimental thing, we're always doing it in mass because it's always easiest for us to measure in mass. But in reality, things are reacting in molar ratios. So we're always using that molar mass formula. Okay, and then determine the percentage yield of this reaction. What I want you to do, I want you to pause the video here. I'm going to pop the answer up on screen. I won't go through it just because we don't have a huge amount of time. And you can double check that you've got the right answer. Okay, so I've got the answer for part A up on the screen. So all I've done is I've just used that molar mass formula to work out the number of moles of this product that's reacting. Then once I've worked out the number of moles that are reacting, I've then looked at the molar ratio. And then since this is a 2-to-2 ratio, because these stoichiometric coefficients are 2 and 2, then since I've got 2 moles of magnesium, that means I must have 2 moles of magnesium oxide as well. So that's how I've worked out the number of moles that have been involved in the reaction. And then since theoretically there's 2 moles, then there should be 80.6 grams of the magnesium oxide produced. So now what we're going to do, since we've worked out that 80.6 value, we're now going to work out the percentage yield of this reaction. So I'm just going to do this one real quick. So the percentage yield is equal to the expected yield divided by the theoretical yield times by 100 to make it a percentage. So the experimental yield, what was the experimental yield? 18 grams. So 18 divided by, 80.6 times by 100. Just going to quickly pop it in my calculator. 80. And my dog's coming to say hello. Hello, dog. Sorry, I just had to pause the video there to let her out so she can go to the toilet. Where was I at? Yes, this percentage. Okay, so 22.33%. So not a super great yield, but you know what? It is what it is. All right, so here's this question here. So this question is similar. And again, we've got an equation there. Just quickly double check that it is balanced. Determine the theoretical yield of carbon dioxide formed when 10 grams of C7H16 is burnt in the presence of excess oxygen. Okay, so what I'm going to do is, again, I'm just going to just quickly write up all of the information and then I'll come back. Oops. Okay, so I've just gone through and I've worked out the mass or the theoretical mass of carbon dioxide that we're expecting to produce. So just use my my mass and my molar mass, substituted that into my molar mass formula to get the number of moles of this compound here. Now, I had a look at this chemical equation, and if I have 1 mole of this, that's going to produce 7 moles of carbon dioxide, so effectively 7 times the amount. So all I've done is I've just multiplied this 0.1 by 7, and so that's told me the number of moles of CO2, and then again I've just substituted into that molar mass formula to find this particular value. So that's our theoretical yield. So the chemists that analysed this reaction produced 25 grams. So let's go ahead and do the percent yield. So the percent yield is equal to our experimental yield divided by the theoretical times by 100 to make a percentage. So we had 25 grams of product, and out of a predicted 30.8 times by 100. So quickly chuck that in my calculator, 25 divided by 30.8, and then times 100 to make it a percentage. Oops, I divided by 100, that was the wrong way. Times, let's try that again, shall we? Times by 100. 81. 81.17%. That's a lot better. Alright, so the percentage yield for this reaction is 81.17%. Okay, last one. So, wine bottle has a defective seal. The ethanol becomes exposed to oxygen. By the way, not that you guys are like wine drinkers or anything because you're all like 15, 16, 17. But just to let you know, in the future, when you're an adult, if you take you open up a bottle of wine and you go to drink it like a week later, it's not going to be good. Wine is not something that stores well once it's exposed to oxygen. It basically produces this compound, acetic acid. Oh, look, it mentions it here in the question. And that's basically vinegar. So if you are someone who, when you are older, likes wine, I'm afraid you just have to drink the whole bottle at once. And there's a scientific justification for you doing so. All right, so I'm going to go ahead. I'm going to construct the balanced chemical equation off screen and I'll come back. Alrighty, so balanced reaction, actually really simple. It's all a 1-to-1 molar ratio. For question B, obviously ethanol is going to be the limiting reagent. There's only so much ethanol in a bottle, but there's a lot of oxygen in the atmosphere. And I want you to go ahead and investigate some methods used by winemakers to prevent this reaction from occurring. All right, guys, I will see you next time. Have a good day. Bye.